This video is going to cover vision systems. So there's a few links here that I recommend that you go to and check them out. I'm not going to go into these in this video. Okay. Definition. What is computer vision? Computer vision is a field of artificial intelligence that enables computers and systems to derive meaningful information from digital images, videos, and other visual inputs. They can then take those actions and make recommendations based on the information. If AI enables computers to think, computer vision enables them to see, observe, and understand. Okay, so this definition came from this IBM website here. So when you talk about a vision system, right, we're talking about for some type of computer or controller or robot. And the vision system is going to have one of 5 major tasks, or maybe multiple of these. First one is part identification. So you want to identify a part or try to classify a part. Then there's part location, part orientation, part inspection, and range finding. So we'll look at each one of these here. So first, part identification. You want to apply for industry and manufacturing. We're going to look at that in the next few slides here. But for just being able to identify things, this is, a lot of times you've been heard of things like facial recognition and things like that. So this is really on the upper level of AI or artificial intelligence. So number one, we're looking at an object. We want to classify it, identify it, detect that it's there, possibly detect like landmarks, segments, meaning certain areas of the image we might be looking at, and just recognition. All right, so kind of demonstrate that over here. So we have this image and we can classify this as a cat. Okay, so that's classification. Now here we've got classification and localization. So not only did we classify it, but we've kind of specified where in the photograph it is at. Okay, and then over here we have object detection, where we're just detecting different objects in here. And then instance segmentation, this is where we're actually just kind of trying to crop out and identify, okay, this is that. Instead of just over here with the localization, we're like, okay, it's in this area. Here we're saying this is all, these are the images or the pixels within the image that make up this particular object. Alright, so when we look at manufacturing, usually for like robots or whatever, we want to identify parts. So what we're looking for is to see if the part is there or if the part is correct. So we might want to do like inspection of the parts. A lot of times we just take a look, take an image, a picture of the part, and compare that to a known part. Sometimes this is referred to as error proofing. So here you can see that we have 2 objects. The one here in the center has a circular hole in the center, and the one on the right then is just a rectangular hole. Other than that, the 2 parts pretty much look identical. So the question then becomes, do we care what shape the hole in the middle is? Maybe we don't, and so then we would say the 2 parts are identical, but on the other hand, maybe we care that, this one's a square hole or a round hole, and so we need to know that, and so we're comparing, and if we're concerned about that center hole and we don't want it to be square, then we are going to deny that part or mark that part as bad. Okay, So once we teach it to identify the part, the next thing we can do is try to identify the part location and or the orientation. And so to do that, we have to do what's called a calibration. So we use a grid. Usually the grid is a set of dots that are evenly spaced apart. And so we need to know exactly how far apart those are, and that's part of the configuration. But then once you have that, you calibrate that grid into your system, and so it knows the size of the object, and then it can also determine the how far away where the object is at. So like if this is our reference point up here in the top left, we can count how many dots over and how many dots down, and we can also determine orientation. So these two can usually be determined at the same time. Okay. Now that grid is not needed once the system's been calibrated. Okay. So once you put the grid on there, you take the picture with your camera, and you know where the grid is at, and you calibrate that so that the system understands where that's at in the image of the camera, and then you no longer actually need to have the grid. So the grid doesn't have to be there when it takes the pictures of the objects. So along with the part and identification, we can also do part inspection. The difference here is that we are looking at, we have to use it like a grid to specify the size of the parts, and so then we can then measure the size of the hole or the size of the part. Okay. So when you do this, like I say, you know, because you've used a grid to calibrate, and again, the grid doesn't have to be there once the calibration has been done. You can remove the grid, but this will specify like the size of the part, the size of the hole in the center, or whichever aspects you're looking at. Okay. And the fifth one there is for range finding. So the views we looked at before were just like for 2 dimensions. So you're looking at the size of the part and the orientation or the location of the part in a 2D plane. So you have like the surface that the part is sitting on. But with range finding, the idea is that not only can we find the orientation and the X and the Y location, but we can actually also detect how far away that is. Now to do that, you're going to have at least 2 camera views. Now notice I use the term views here, which means that if you have like a robot and the camera is mounted on the robot, then you can have the robot move the camera and take 2 different pictures with the same camera. And so that's why we're using this term views here. You can only have, you don't have to have 2 cameras if you have a camera mounted on a robot that can move. The other thing that is even way more accurate as far as determining this distance of how far away the object is a laser. So a lot of 3D type cameras, a lot of times they'll have like a camera and then 2, sometimes more than 2 lasers attached so that they can accurately measure the distance. So if you look like at a robotic vision system, which is pretty much true for any vision system, obviously you need a camera, you need a camera controller, you need the interface equipment like the the cables that are going to connect it and power it, that kind of stuff. You need a monitor and a light source. Okay, lighting is very important when you're talking about being able to identify something, right? If it's in pitch black, the vision system's probably going to have trouble seeing it unless it's like an infrared camera. So now the monitor here is more for us to view it and teach when we're trying to train or teach the vision system, what we want to look for, we need the monitor. Once we've taught the system, we don't really need the monitor. It's kind of nice to have so we can kind of watch it as it works, but we don't actually need it to be there. Okay. When you talk about the camera, okay, you have like the body of the camera, which has the CCD, which is referred to as a charge coupled device. This what this means is that the intensity of the light um, charges these. It's usually made up out of photoresistors or photodiodes, and so the light needs to hit that. But then you also have the lens, and then there's something called the focal length. So the focal length is the distance between your CCD and your lens focal point. And then you have what's called the standoff distance, which is how far away the object is that you're taking the picture of, or at least the total surface distance to the camera, and then that specifies your field of view. So it specifies how much the camera can actually see. So if you have a different focal length, if you change the focal length, or change basically your lens, then that's going to affect your field of view and your standoff distance. All right, so this CCD, or charge coupled device, right? This is what a digital camera actually uses to absorb the light and therefore produce the image. Okay. And so this charge coupled device is really an array of either light emitting, or not, what they call photodiodes or phototransistors. And so what we have here, down here at the bottom, is a semiconductor, which is made up of like a bunch of photoresistive transistors or diodes, which means that when the light hits it, it allows current to flow through these devices. Now, if we are going to do a colored camera, then what we do is we actually make use of a grid of a filter here. So we have blue, red, green, and blue. Those are our primary colors that give us control the light. And so what we have is, for each one of these, we have a red, green, and blue transistor, and that's called a pixel. So each pixel is a single cell, and if it's just a black and white camera, it's just measuring the intensity of the light. But if it's a colored camera, it's actually going to have three, it'll have like this filter here, which will then filter the light to give us a red hue, a green hue, and a blue hue, so that we can then look at the intensity of those three different colors and therefore determine the actual colors of the system. Alright, so if we're just looking at, say, a black and white camera, then we just are looking at the intensity of the camera. And so for like a standard camera often used for robots, what this basically does is it's a 8-bit camera, which means that it has an intensity of 0 to 255. Okay, so you have shades of gray. So if it's 0, then that's black. If it's 255, it's white, and anything else is just like a shade of gray. So blue or green or any other color is just showing up as a shade of gray inside of a black and white camera. So the imager chip then is this array of these photosensitive devices that are, and then it's converting those into pulses, into ones and zeros, right, that are then fed to the controller, and they're fed in this array, which gives us the entire picture. So these, each one of these little photosensitive diodes or transistors that are there are referred to as a pixel or a picture element. Right? The standard camera for FANUC robots, just for 2D vision, no lasers or anything like that. One very common camera, anyhow, is this Sony XC56. It's the one we have in the classroom for our robots. And it only actually has an array of 659 pixels for, and then 494 in the vertical. Okay, so this actually only gives you a total of about 325 pixels. So a lot of times, like when you get a cell phone or whatever, you're looking at the camera quality on the cell phone, and it's like something like 8 megapixels or 12 megapixels. That means 12 million pixels. This right here camera, like I say, which is very commonly used currently on robots, is only 1/3 of a megapixel. Alright, now when you have a dot of light and it's falling on these photodiodes, okay, then you kind of get into, okay, you actually have an array of these little diodes, right? So you have just kind of like these little squares of these diodes. And so if you have the intensity of light focused right in the center of a pixel, then pretty much that entire pixel gets bright. And so now you have that pixel is bright, but everything else is dark around it. Now, if you have poorer resolution, or the circle gets larger. In this case, I guess the circle's getting larger. So now the circle was just enough to just cover up that one pixel element, picture element, pixel. And then here it's a little bit bigger than it was up here, and so now you kind of see, you have this bright spot, and then you have these four here kind of get a little bit of light on them because the circle is bigger. And then as the circle gets even larger, right, then it's covering, a wider array of these pixels, right? But now, so like this is here where the pixel is very, or the light source is very bright, but centered on one pixel. And then as it gets larger, it kind of carries over to these other pixels. But now over here, we have that same light source is now at the corner of 4 pixels. So instead of having one very bright pixel, we actually have 4 pixels that all are kind of a shade of gray because they all have about the same amount of light on them from this centered source. And then of course as this gets larger, it's still just on these 4 pixels, but they're brighter because they all have more intensity on them. So if we go to the colored camera, again we have these filters on top of these photo diodes or photo transistors here, but each one of them again is typically 8 bits, which gives you that range from 0 to 255. But if the light source is green, then you get a green pixel, and but the blues and the reds aren't affected by it, and so on. Alright, so here's some examples if we're trying to identify the letter H. Okay, so we have like a black H showing up on a white surface. Okay, so and this is just a very low resolution 8x8 array here, just kind of trying to demonstrate, which pixels are being identified here. So in this case, like all these squares are all white because they're just reflecting light. And then you have this black H, which isn't reflecting light, and therefore you have these darker pixels. Now, when you have lots of pixels and you're trying to identify a straight line. So let's say that we have this red line, um, or actually the green line. Let's say that we have this green line. If we have the green line, but we only have a few pixels, then it's kind of hard to tell exactly the angle of it. Okay, so as the angle of the line, as you use more pixels, you can actually like identify the angle of the line better, right? So that's the resolution of the camera. The more pictures, the more accurately you can kind of tell the shape of an object. All right, so that again, that's kind of like the resolution of the camera, okay? And also has to do with the field of view um, of the camera. So if you have the object is closer, then it's going to be larger within the camera image. So if we go back just to the black and white camera here, we have the black, right? If it's a 0 is black, it's 8 bits, so 0 is black. You get like a middle gray at 128, and then as bright as the light's as bright as the transistor can handle it is 255. Now, pixels basically have two properties. They have the brightness, but then they also have the location inside the array. So when we're trying to identify where a part is, right, we're looking at which pixels are bright and where they are in the array. That's how we can tell the rotation and the location of the objects. All right, so the edge of a part, um, when you're trying to identify a part, you're really looking at the edge of the part. Okay, so you're kind of trying to see where the difference between light and dark is, right? And so your cameras are really identifying um, edges of parts. And so over here you can see we have these two different parts. They have some holes in them, I guess, but they're clearly separated, so you can tell the difference between them. But over here the two parts are overlapping, and so it's harder to tell the difference between those. This is a picture showing that edge there. So again, the camera is basically identifying the edge. So down here on the bottom we have the old zeros because you have this like dark object that's not reflecting any light into the camera. And then up here you have full reflection, the 255. And where the edge of that piece goes through, as it goes through different pixels, these pixels have odd values, right? They're not 255, they're not 0, there's something in between. And so that's what it's really detecting, is the edges of this object. Alright, so we also talked about the range part here. So you see, like over here I have a template where I'm like teaching it the letter C. Okay, and so I have this letter C and I can show it that. But now if that C is further away or closer or rotated here, then it may not be able to detect that. Okay, and so again, this is really talking about a 2D camera, right? This is the where a 3D camera, using multiple views, we can then detect maybe how far away that is. But if we're using just a standard 2D, we can't detect if the part is further away, okay, or it just looks, it's smaller than what we were trained. So this is what we were trained. We trained the robot to identify this, and even though this is the exact same shape, it's not the same size, so the robot doesn't think it's the same part. Alright, so then we have the controller. What we do is the controller is the computer that is looking at the image and comparing the images. So the first thing we have to do is train it by giving it one or more images to, so we have to teach it this, we're looking for this C, or you're teaching it the part. Okay? And then, so the controller obviously has to have memory so that it can store these images, because we're going to store these images, and then it's going to talk to the camera, take the picture, and then compare it to what it's stored. And then of course we have like the power supplies and cables, things like that. Now lighting is extremely important for vision systems. Okay, there's three major different lighting techniques that are used. I guess a fourth one not mentioned here is just filtered or colored lights. Okay, but we have front lighting. Front light here, you have the camera, and then you have a light shining down on the object, and then you're trying to identify again the edges of that part. Front lighting is good. It's simple for the most part. It's usually the simplest, and it's does good for stationary or slow moving parts. Okay. Backlighting is really good to help establish the edges. Okay, so if you actually put the light behind the part, then you get a much darker, you're not getting any reflection. So the problem with front lighting here is you're actually getting reflection even if the part was, black or just very dark color. You're going to get reflection of that into the camera. Where if you have the light behind the object, then you're not going to get any light at all. So it's going to be definitely, just absolutely black on those pixels that aren't getting any light at all. So it's very, very good for inspecting, especially inspecting the edges of the part, or looking for like the size of holes, or shapes of the holes, things like that. And then we have structured lighting, okay, and structured lighting, we angle it. This is often done with a laser, and the idea now is we can actually tell the shape of the object. Alright, so using lights, obviously we could use like an older incandescent bulb, fluorescent bulbs, or we can use a laser. But the other big one is a strobe light. So strobe lights are very good for fast moving objects, because the problem is when you try to take a picture of an object and it's moving, right, you're going to get a blurry kind of, okay, well, it's moving, but it's blurry, so it's really hard to detect edges, especially, or if you're trying to scan a barcode or something like that. But if you use a strobe light, it pulses, and so you can actually, it makes it look like it's not moving, and so you actually get a much cleaner image of that object. It looks like it's like still, like it's not moving. And then of course the shapes here with the lasers. Alright, so here's just some examples of the backlighting. So here at the backlighting we have a light behind the object, and then we can very clearly detect that there's a chip out of this object. Okay. Now you can also kind of tell the type of surface if you used angle lighting. So the idea is if you have a smooth object and your light is coming off at an angle, um, and it's going to reflect at that exact same angle. However, if your surface is rough, some of that light will hit like a high peak and get reflected in the opposite direction. And so you can actually detect some surface roughness, or get an idea of how smooth or rough the surface is by the diffusion of the light. All right. Colors also have a huge effect on this. All right. So color, you can use colored filtering, and you can get some really different effects here. So see here we're using a green light, and we can see the word Fanuc, which is in red, right? Fanuc's traditional, the Fanuc robot, their trademark color is red. And so if I use this green light with a black and white camera, I can see the word Fanuc very clearly. However, if I use a red light, I can barely see it at all. You can just barely see the C in here. All right, so here we were working on a jigsaw puzzle, and we had these pieces and some different um, trays. And as you look at these, you see that this blue, for instance, you can see this piece here is clearly a much lighter colored brown, where these other pieces are almost black, and this has maybe a little bit of brown on this one edge. But looking over here, you can kind of see the brown on this one, not too bad. Over here, I can hardly tell the difference on those. So this is, again, just kind of showing how colors can affect the look of an object. Now, these next set of slides actually were provided by Intel and for artificial intelligence here. So, the idea here is looking at the difference between human vision and computer vision. Okay, so again, the idea is with computer vision, we have to teach, we're going to teach the computer to identify the part. And so, we have like, for the human brain, we have this object. It's like, okay, we see that object, and then our brain makes the connection to say that that is a cat. And so the question, I guess, becomes, how do you know it was a cat? Well, we had to learn that. Somewhere along the way, we learned that that object is a cat. And so that's what we have to do with the vision here. Okay. So remember that the computer is just looking at numbers. Okay, so we have this CCD is capturing this data, and we see bright numbers, and then we see darker numbers due to the shades on the image. So, this is just kind of, some of this is just repeating what we already talked about with the pixels and stuff. Now, as I mentioned, 3D vision system, we're actually able to determine how far away it is, and a lot of different aspects here. So what I wanted to really show you here in these slides is to get into this AI aspect. So we're looking at classification here. So we have like various different animals, and so the question then becomes, can we, if we have an image and we teach the computer what a dog is, what a cat is, what happens when you get some other object in there? If you've never taught it what an eagle looks like. You know, it's like, well, hey, I see some white here. The cat's white. Maybe, you know, maybe this is a bird, or maybe it's a cat. That kind of stuff. So there's this online tool. There's this online tool called Teachable Machine, and so we're going to actually be using this in the lab. So the idea is, again, what we have to do is we have to actually teach the computer by giving it some images, and then after we train it, then we can feed it some images it's never seen before and see if it will be able to identify those objects. So that's what we're going to be doing in the lab this week.